Okay, we just started the CPU design, and today we are going to finish up. Okay, yes, you heard it right. Yeah, milestone number 2. Yes, due is tomorrow. Yes, due is tomorrow. So it is labor intensive, but it just take time, right? So that will take time. So to refresh, okay. So to remind, the second milestone due is tomorrow, right? So it is about drawing schematic diagram. Right? The skeleton design is given to you. So your job is to draw this schematic diagram. So as detailed as possible. Here, a CPU, block, right? Here, memory, right? Input, output ports. And you need to draw the structure of this CPU, right? And this assignment is for you actually, for following milestones. Following milestone number 3, 4, 5, 6. Probably you have to use this drawing as your reference. You take a look at your drawing and find out the spot you have to modify for the milestone number 3, 4, 5, right? So this will help you a lot. So what you have to do is try to draw a schematic diagram as detailed as possible and as neat as possible, as clean as possible, right? That because you are going to use that drawing, right, for the following milestones. Okay, so no one is going to take a look at your milestone, take a look at your drawing. You are going to look at your drawing. So my suggestion is do not use pencil and paper to draw this schematic. Try to use some computer program. Okay, PowerPoint is okay, but I don't know if it is that convenient. So Visio, I don't know. Visio, some other convenient drawing tool for you, right? Try to use that computer program because you have to modify your drawing a lot later on. If you use pencil and paper, you have to use eraser, right? Erase something, draw something. It eventually it will be very dirty. So again, this milestone is for your reference. Okay, so uh, try to draw as detailed as possible. Detailed, organized, clean, neat. Okay, and that will help you a lot later on. Okay, any other question? By the way, if you have webcam, please turn on. Why don't you? Right? I want to look at you. Right? Okay. So again, we will finish up CPU design, right? Yes. So CPU design is that simple. Okay. So we will finish up CPU design. So last time, to refresh your memory, last time we finished instruction patch logic. I remember this one. This logic, program counter, adder, and Verilog description. Hardware design. Right? This is not software program, right? This is hardware design written in Verilog HDL. Hardware description language, HDL, right? HDL. Hardware description language, right? You are describing hardware using this language, right? Verilog HDL. So you are designing hardware, not software, right? So memory, okay, memory, we are using Altera, Intel FPGA. So Intel FPGA, right? That Cyclone 3, Intel FPGA specific memory, right? So I created that memory for you. So that is the one. RAM 2 port, instruction data memory. Okay. So using the CAD tool called mega wizard. I created that memory. And the important thing is, if you go next, here, memory initialization tab here, mem initialization, I specified, okay, that memory will be initialized with that file, inst underscore data.mif. MIF stands for memory initialization file, memory initialization. So again, Eclipse, right? So if you compile your assembly or C program, then MIF is generated automatically for you because I wrote, Perl script. Right? I wrote this Perl script, these two. So Perl script will take the compiled binary and give you this MIF. Okay? So that is where we were last time, right? So here, now instruction decoding. Okay, Cheon, can you please?
Instruction decoding. Instruction decoding separates the fetched instruction into the fields according to the instruction types, R, I, S, B, U, and J types. Opcode function 3 and function 7 fields determine which operation the instruction wants to do. Control logic should be designed to supply control signals to data path elements such as ALU and register file. Operands, register numbers in the instructions are sent to the register file. Immediate field is the sign intended depending on instructions.
Okay, thanks. Decoding step, right? Once you have instruction inside the CPU, once you have instruction patch it, okay. Once you have, let's say, addition instruction, addition x2, x3, x4. Once you have instruction inside the CPU, then the next obvious step is instruction decoding, right? So what is this instruction for? So you have to figure out, right? By interpreting that instruction machine code, right? You have to figure out, okay, I need to do addition or subtraction, right? You can tell by looking at opcode, function 3, function 7 field, right? By looking at these three, CPU can figure out, okay, I need to do addition operation, okay? By looking at this, you have to generate control signal, okay? Some examples of control signal, okay? Some simple example is you have to generate ALU control signal because ALU is able to do many different operations, right? What operation? Okay, in this case, please do addition, right? Some control signal. And then register file, write enable. Okay, that instruction is updating register file. Yes, X2, right? Register should be updated. So that control signal should be asserted, meaning should be 1. So, those are examples. Those are examples of control signals. So first thing, in decoding step, you have to generate all different control signals, okay, which are used inside the CPU. And second thing, operand preparation, source operand preparation. Okay, so in this case, you have to prepare X3 and X4. Okay, these two registers are supplied from register file X3, X4. So operand, source operand preparation, two things, control signal generation and source operand preparation. Okay, that should be done in decoding stage. So let me show you schematic. Okay, so that is the encoding, right? Instruction encoding, R type, I type, right? OP code, same location. Function 7, okay? The first 7-bit. Function 3 in the middle, 3-bit, okay? By looking at this orange field, you can do the decoding, okay? Okay. So let me show you schematic diagram of decoding logic. So that is instruction patch logic, instruction patch, okay? So based on that program counter, instruction memory, right? Memory can provide machine code instruction, right? Machine code is providing instruction at that location. Okay, example, addition operation, for example, right? Provide instruction, and then the digital logic from the instruction, from the machine code, you can take out. Look at this. You can take out RS1, RS1, RS2. Okay, these 5 bits, next 5 bit. You can take out using digital logic, right? And supply, connect that to register file. Okay, register file. RS1, RS2. First source operand, second source operand. Then register file can provide, source operand, register. Okay, and then destination location, RD, can supply to here also, RD. Let me show you. In case of R format instruction, you have to provide destination register number, RD2, right? RD. And then depending on instruction, you need to do sign extension. Okay. So example is, in case of I format instruction. Okay, look at this. Second source operand. Okay. So example, to give you better view, add I instruction, right? X2, X3, some constant, some immediate, right? So first source operand is coming from register file, but second source is included in the instruction itself, immediate. So in this case, R type instruction, R type, and this one is I type instruction, right? R type instruction, first source, second source are coming from register file, both, right? But here, one is from register file, the other is in immediate, right? So depending on instruction, okay, some instruction, two source operand are coming from register file, but some instruction, you need to take immediate and do sign extension, okay, to provide 32-bit data, to generate 32-bit data. Okay, that will be second source operand in case of I format instruction, I format encoding. Okay, so that is source operand preparation. Okay, and second thing, control signal generation. So this control unit, this hardware unit takes these 3 field, OP code, function 7, function 3. And by looking at this control unit hardware can generate all different control signal. So in this particular schematic diagram, we have only one control signal here, write, enable, register write. So control unit will generate reg write control signal. Okay, does it make sense? Again, decoding stage, control signal generation and operand, source operand preparation. Okay, let's design that component, sign extension logic. How to design sign extension logic in hardware? So because I showed you, right, register file design a long time ago, right? I think 6 weeks ago, I showed you. So let's skip register file design and let's design a sign extension logic. Okay, I'm going to skip this slide because we already did that. How about sign extension logic? Hardware design is super simple. Look at this. You are taking input, okay, 12-bit input, and output is 32-bit. So you have to do what? Sign extension by looking at MSB, by looking at most significant bit, right? Sign extension logic. Okay, taking immediate 11 to 0 and provide 32-bit immediate 3120. So by looking at MSB, right? Most significant bit MSB, right? Most significant bit. Sign extension logic can duplicate, okay, this MSB 20 times, right? 20, right? 12 bit, and 20, right? 20 duplication. Then, 20, 12, 32 bit, right? So how to design that in Verilog? Very simple. Look at this. Sign extension, input, right? 12-bit input, A, 1120. Output, 32-bit, right? 3120. Okay, you specify input and output, then you describe, right, using language, the behavior. What is the behavior, right? Output is equal to, look at this one. This one is called replication operator. Replicate, 복제 in Korean, right? Replication operator. How many times? 20 times, right? 20 times, replication, right? 복제, right? And then what? And append, A. This one, append, right? This one is concatenation operator. This out, curly bracket, outmost, curly bracket, this one, and this one. That is concatenation. I'm very bad at spelling. Concatenation operator. So you want to append, attach this one and this one together, attach. So 20-bit, replicated 20-bit, and 12-bit, right? Original 12-bit. So just attach, connect, attach. So that outermost curly bracket, opening curly bracket, closing curly bracket, outermost. Okay, that is 32-bit. So signing extension, that's simple, right? So if you are curious, you can send it. You can send it to Quartus to see what kind of hardware it generates. By using this reference, okay, class project, skeleton code. Let me overwrite everything, okay? Select everything, okay? Just leave this sign extension, copy and paste, right? And again, you have to be careful. This module name should be same as this project name. That is a restriction, Quartus restriction. You have to follow that. Otherwise, let me try to compile it to see what happens. It refuses to synthesize. Okay, it refuses to synthesize. Name is different. Okay, so all you have to do is change that to RV32I system. Okay, this is a tool, this CAD tool specific restriction. Okay, CAD tool specific. Quartus specific. So if you compile it, synthesize it actually, right? Hardware generation. Okay, you synthesize, okay, right? No problem. Okay, then take a look at this RTL viewer. Okay, click this. It is generating rough schematic diagram. In this case, it doesn't show any useful information. But think about that. What is sign extension? It is super simple. If you draw schematic diagram yourself, this logic. So how would you draw that schematic diagram? I would draw like this. Okay, you have 11 input, starting from immediate 11 to immediate, just wire, right? Wire, input, wire, 전선, right? 전선. Then what do you have to do? Sign extension. Copy, right? Replicate. How many times? 20 times. That's it, right? That's it. That is output, right? Output or output. 32-bit output. That's it. Super simple, right? Sign extension logic. No brainer, right? Just connect, right? Tap this line, tap this, MSB, and generate, create so 20 more lines than 32, right? That is sign extension logic, just wires, right? So, and we don't want to draw that schematic. That is why we use, language, right? Language, this description. Okay, that is sign extension logic. So if you go back to here, so we now know how to design instruction fetch logic, how to design register file, how to design sign extension logic. We will talk about control unit later on, not this PowerPoint, next PowerPoint. Okay, we will talk about that control unit. Okay, then let's move on to what? Execution step. Right, this one. Now we interpreted machine code. Now next step is execution. Okay, now let's move on to execution. And we have three, three big instructions, right? The first one is data processing. Data processing instructions like addition, subtraction, and or. Okay. Second, memory access instructions. The last one, branch instructions. So we will talk about execution unit for each instruction category, right? First, data processing first, and then this one next, and this one last. Okay. Data processing instruction first. This one, Sujin, can you please?
Can you hear me?
Mhm.
Instruction execution 1. Execution of the arithmetic and logical instruction. R-type arithmetic and logical instruction. Two source operand from the register file. I-type arithmetic and logical instruction. One source operand from the register file. One source operand from the immediate field.
Okay, thanks. Data processing instruction is using R-type encoding. If you recall your memory, okay, data processing instruction is using R-type or I-type encoding. So you have to take a look at this encoding, instruction format. Okay, so first, R-type instruction, look at this, most complicated encoding, right? You have how many? 1, 2, 3, 4, 5, 6 different fields. Okay, and I-type 1, 2, 3, 4, 5 different fields. Okay, so these two are example, add I. So what is the difference between these two? By looking at this encoding, everything is the same except second source operand, and also function 7, right? Function 7 is different, but the biggest difference is in case of R-type instruction, two source operands are coming from register file, S1 and S2. But I-type data processing instruction, one source is coming from register file, this one, S3, and second source is coming from instruction itself, immediate. That is the biggest difference, right? So when you design execution unit, you have to think about that. Then what do you have to do to prepare to, what do you have to do to, send source operand to ALU? Okay, so let me show you here. So that is a decoding, right, logic. So, the most obvious, the component in execution unit is ALU, because ALU is doing all different computation, right? So you have to have ALU for execution. Then the question is, how do you have to connect these three 3, 2 from register file, 1 from immediate, sign extended. What you have to do, what kind of connection you have to make? You have to connect, right? How do you connect these 3 into ALU? So, first source operand is always coming from register file. You can directly connect register output to first ALU input. Because if you go back, first source, S1, right? S1, RS1, RS1. First source operand is always coming from register file. So you can directly connect register file output to ALU. But the second source, look at this. Second source, R type, RS2 from register file. But second source is from instruction, immediate. So what do you have to do? Here, you have 2 candidates, right? First one is from register file. Second candidate is from immediate. These 2 guys are competing for one ALU input, second input. Then what do you have to do? You have to add some hardware component. What? Multiplexer. Right? Multiplexer is doing selection. Right? Multiplexer and connect like this. Okay, connect like this. 2 guys. These 2 guys are competing for this second input, ALU second input. So by adding this multiplexer, you can select which one, this one or immediate to ALU. So adding multiplexer means you need to have control signal, selection signal like this, ALU source. Who do you think is generating this control signal? ALU source. Who do you think is supposed to generate control signal? Control unit, right? Control unit, right? How come? Because control unit knows, right? By looking at OP code, function 3, function 7, this guy know, okay, this is R type instruction. Or, okay, this is I type instruction, right? R type instruction, ALU source. ALU source should be 0. 0 meaning multiplexer is selecting first input to output. In case of I type instruction, multiplexer supposed to select second input immediate to ALU, right? So ALU source supposed to be a 1, right? 0, 1. So let me show you like this. Multiplexer. In case of 2 to 1 multiplexer, this one is 2 to 1 multiplexer mux. Selection. Select. If select is 0, then you are connecting. You are simply connecting this guy to output 0. Okay. And selection is 1. Selection is 1. Then you are connecting. You are connecting second input to this output. Very simple logic. 2 to 1 multiplexer. 2 input, 1 output. Right? 2 input, 1 output. Control signal. Right? So control unit can tell you by looking at this operation code. By looking at operation code, control unit can tell you. Okay. Then ALU output, right? ALU output supposed to be connected to register file. So register file ALU output, data, and destination register. Okay, write this data to that register. Okay, to the destination register. Okay, so this one is complete CPU actually. This guy is able to execute all or data processing instructions, addition, subtraction, and or. Any question about this? Okay, then let's design, multiplexer. How would you design multiplexer? Very simple, right? If you use language, okay, one more thing. Here, again, ALU is able to do many different operations. So you have to tell ALU, you have to tell, okay, do addition operation. Please do subtraction operation, depending on instruction, right? Depending on machine code, you patch it. So control unit generate control signal for this ALU. Same ALU control, ALU control. Okay? That is connected. It is physically connected, right? So I don't want to connect to that, ALU input because it is going to be very messy, right? If I connect, to here, if I connect ALU source to here, it is going to be very hard to read and messy, right? So I don't want to, same name connected, right? ALU source, ALU control, ALU source, those are connected. Okay. Okay, then how would you design multiplexer? A 2-to-1 multiplexer, very simple. Look at this description. So here we think input D0, D1, and select S, and output Y. And that is 32-bit. 32-bit, 32-bit. So, if you look at this, you specify input and output first, right? Here, D0, D1, S. 3 inputs. D0 input, D1 input, selection input. Right? Output, 32-bit. Output 32-bit. Specify input and output, simple, right? Then describe each behavior. It's just like C code, right? See, probably, C is providing this keyword, right? Depending on S, depending on selection, right? S. Which one do you want to select? Question mark, right? Which one do you want to select? S is 1, then you are selecting first one, D1 to Y, D1 to Y, right? Selection is 0, then selection is 0, you are connecting D0 to Y, right? You are selecting D0 to Y. Very intuitive description, right? By looking at this, you immediately know, even though you don't know the syntax. Okay, it sounds like depending on S. Okay, you are selecting D1, D0, right? Very, very, intuitive, simple description. Is it combination logic or sequential logic? Combination logic, right? What is combination logic? Output depends only on current input, right? If you supply D0, D1, S, then output is determined only based on current input. There is no, storage component, the memory component inside the multiplexer. No memory, right? Based on this, then output is determined. So this is one way to design multiplexer. You can use, other keyword in Verilog. Same multiplexer can be implemented, can be designed with using always statement. Always. So that is another way. One way, there are 2 different ways to design combination logic using this assign keyword. And second, using this always keyword. 2 ways, right? So look at this description first. Selection, right? Also very intuitive. Is it like C code, right? Selection is true. True means what? True means 1. Then Y1, D1. D1 is connected to Y. Otherwise, Y, right? Output D0 is connected to Y, right? Even, more intuitive, right? If else statement. Okay. What is this one? Asterisk. Always always do begin and end. Always do this. Always do this. When at this time. What is this time? What is that? Asterisk. That means it is called sensitivity list. Sensitivity list. Sensitivity list. That means whenever input signal gets changed, then do this again. Do this again. What does that mean? Whenever input signal. What are input signal here? Input. Look at this. D1, D0, S. Those are inputs. Right? If you look at this always statement. Input again. S, D0, D1. Those are input. What is output? Y is output, right? Output. So that asterisk means whenever input changes, S or D0, D1, those got changes, then do this again, evaluate this again. That is, also very obvious, right? Look at this. Whenever this guy changes, then you have to evaluate that again, right? Output will be changed also. Try to understand, try to think about this hardware component, right? Then its behavior. Okay, input gets changed, right? Selection is one, for example. Data is what? Data is here. Let's say 1, 2, 3, 4, 5, 6, 7, 8. So this one, let's say 0, 0, 1, 1, 0, 0, 2, 2. Then this guy got changed to 1, 1. Selection is 0. 1, 1, 0, 0, 1, 1, 0, 0. This got get changed, right? Then output should be changed because selection is 0. That is connected. That got changed, right? Then output should be reevaluated because that's supposed to be output. So try to feel, okay? That is important. Try to feel that, try to feel the meaning of this statement. Don't just write, feel it. That is important. To be an expert, you should be able to feel it. Otherwise, you are not expert, right? You should be able to feel it, right? Okay, you understand with your brain, but you have to think twice. Then that is not expert. Okay, I can feel it. Okay, then that is expert. Okay, that is a feeling, right? Okay, so okay, try to feel, then you become the expert, right? Feel with your heart, expert. Okay. So okay, so there is one, either use assign keyword or always, right? Always to design combination logic. Okay. So then the question is, when do you want to use assign, and when do you want to use always? The rule of thumb is, if the logic you design, logic you want to design is simple, then use assign keyword. If the design is a little bit complicated, then probably you want to use always, because there are several keywords you can use with always. So assign, you cannot use if statement. So you can use, this very simple, right? And also just one line, right? Here, 1, 2, 3, 4, 5 different lines, right? So I don't want to type, right? I'm lazy, I don't want to type. Simple design, just to use assign. Design is a little bit complicated, then use always, because there are other keyword in addition to if. You can use other keywords. Okay, so this one is trying to explain parameter. Sometimes look at this description here. I did not specify the width, right? Here I specify the width 3120, but here I did not specify. I use this the I use this width, right? Variable like word, right? the width -1. So I didn't specify the width, and by using this parameter, the default is 8. So that means 720, but because default is 8. The beauty of using this parameter is when you instantiate, it's like a library. You put this description, this module hardware component in the library. Then whenever you need multiplexer, you can instantiate. Okay, I'm going to instantiate like this. Okay, instantiate. Same name, box2. When you instantiate, you can specify the width here like this. Default 8-bit input, 8-bit output. But if you specify 32, this multiplexer is 32-bit input, 32-bit output. So beauty of using this parameter is you don't have to design separate multiplexers with different width, right? Different input width, output width. Just one multiplexer design. Then when you instantiate, you can specify. Okay? So by doing that, you can avoid some mistake, some design errors. Okay, because otherwise you have to design separate multiplexer. Okay, 5-bit multiplexer, 2-to-1 multiplexer, but 5-bit input, 6-bit input, 7-bit input, 8-bit, many different multiplexer. So it is labor intensive, also error prone. Okay, you don't want to do that, right? So use this keyword parameter. Okay, that is the one. Okay, now, second category of instructions, memory access instructions. Okay, this one. Dongwoo, can you please?
Can you hear me?
Mhm.
Okay. Instruction execution. Execution of the memory access instructions. Load instructions. I type. LW, LH, LB, LHU, LBU. Store instructions. S type. SW, SH, SB.
Okay, thanks. Memory access instructions are using I-type encoding or S-type encoding. Okay, I-type and I-type, S-type encoding. So you have to take a look at this encoding very carefully. Memory read instruction. Example is LW, load word. Right? You are reading one word, right? That is using I-type encoding. Memory write instruction. One example is store word. Okay, that is using S-type encoding. Okay, so the behavior is in the function of LW. You are reading from this memory location S3, right, plus 24, and storing to T0 register. And behavior of store word, right? You are writing this data T2 into that location S3 plus 8 location. Okay, so that is a function, and in case of LW instruction, you have destination register, right? Destination, and but SW instruction, no destination register, right? You are updating memory, not register file, right? So you are updating only memory, so no destination register here. Okay, and then memory location is computed based on RS1 plus immediate, RS1 and immediate. Okay, same for I type, S type, same for LW, SW, but immediate is distributed here. Okay, here one big chunk, one big 12-bit, but here 7-bit, 5-bit, okay, distributed, separated. Okay, so you have to consider that part. Okay, so let's first design hardware for executing memory read instruction. memory read first. LW, this one first. And if you look at this schematic diagram, I cut this line. Okay, remember, we have a connection from ALU output to here. I cut this line. Because if you think about LW instruction, LW X3, okay, it's just one example, X5. Then you want to update. Register file after reading data from this location, X5 plus 4. Reading data from this location and update register file. So memory read instruction also trying to update register file, okay? And data processing instruction, right? Addition instruction, right? Data processing, addition instruction, X5, okay? Data processing instruction is updating also register file. So there are two candidates, right? This guy, in case of this one, the data register file, update data is coming from ALU. Right? ALU is doing addition operation. This ALU output goes to register file. This case, but how about this case? You are reading from memory, right? Memory. So you have to supply address. Address is what? X5 address, X5 plus 4. So based on that, you are reading data, right? Data that goes to register file also. Register file. So there are two candidates, ALU output and data from memory. Two candidates are competing for this input. That is why I cut this line for now. I cut this line. I'm going to reconnect. Okay, I'm going to reconnect later on. So for now, I cut the line, and then what do you have to do? What kind of connection you have to make for data read instruction, memory read instruction? So for first you need to have data memory. So in this case, we have separate memory. This one, look at this. This memory is for instruction. This memory is storing machine code only, machine code. And then memory is storing only data, instruction memory and data memory. We have separate memories. So memory read instruction, right? LW instruction. And then the thing is memory location. This one is S3 plus 24. So here S3 will be supplied through that connection, right? And then 24 immediate, that will be supplied through that connection. So S3 plus 24. So ALU will compute memory location. So that ALU output should be connected to this address. Right? ALU output should be connected to this address input memory, right? Because that is the the memory location you want to read. ALU is computing memory location, right? S3, so S3 plus 24, S3 plus 24. And then in response, right? In response, memory will provide the data. Data is coming in from memory. Okay, data is coming into memory, and eventually should be supplied to register file. But I added multiplexer because I have to restore the connection, the previous connection, ALU output to register file. So you have to make that connection like this. So how to interpret that, right? So this multiplexer, original path, data processing instruction, right? ALU output is supplied to register file through that multiplexer. And in case of memory read instruction, the data you read from memory is supplied to register file through that connection. So that guy is selecting, depending on instruction you execute, depending on instruction, okay? If CPU execute addition instruction, multiplexer will select first input to output. If CPU execute LW instruction, memory read instruction, this multiplexer should select second input to output. Right? So this adding multiplexer means you need control signal, right? So in this case, mem2 reg control signal, mem2 reg, memory to register file. Who do you think is generating this control signal? Answer is already there, right? Control unit, right? Control unit generate mem2 reg, memory to reg control signal. Okay. Yeah, try to think the meaning of this name, memory to register file, right? If control signal is 1, that means what? 1 means, okay, true means memory data to register file. Okay, 1, then you need to select second input. Second this input to register file. This one is 0. That means you are selecting ALU output to register file. Does it make sense? Any question? Okay, this CPU. Now this CPU is able to execute what? Is able to execute data processing instructions and memory read instruction. Okay, LW. Okay, so so what then the remaining thing is SW. What do you have to do to execute? What kind of connection or what kind of hardware component do you have to add to execute SW, memory update, memory write instruction? So if you if you look at the encoding, memory location is computed in the same way, right? Same way. S3 plus 8. S3 is supplied through the connection from register file to ALU. And this immediate is separated. Okay, you have to somehow rearrange this separated immediate into one chunk. Easy, right? Very easy, right? Just connection, right? You have separate machine code, these two separated. You just append these two, right? Then supply that to ALU. So ALU will give you memory location, provide memory location where you have to update data to. Then you have to supply data, right? Data is T2 to memory. So what kind of connection you have to make? First, where does it come from? T2. If you look at the encoding, T2 is coming from second source. So the second, second output from register file, RS2, right? So what kind of connection? Okay. Okay, hold on. This one. Okay. So load what? Okay. So here, then connection you have to make is T2. T2 is coming from register file. So that line, you have to tap this line. tap this line and connect that to okay, memory data input. Okay, so that means you are supplying memory location through that connection, ALU output, and also memory location and data. Okay, write this data to that location. So how about that? Very simple, right? So what we are doing is we are depending on instruction, we are adding some hardware component and make connections. If there is a conflict, then add multiplexer. That's it, right? Depending on instruction, we have to execute some new instruction. You have to add some new hardware component. Then some conflict, then add multiplexer. Some conflict, right? We have conflict, right? Two guys competing for one input. Two guys competing, one. Okay, confliction, right? Conflict. Okay. Now let's move on to the last category of instructions, right? Branch instruction. Okay, we will finish up today. Okay, CPU design. This one. Okay. 민용, 이민용.
Execution of branch and jump instructions. Branch instructions I type BQ, BNE, BLT, BGE, BLTU, BGEU. JAL instruction J type.
Okay, thanks. There are two kinds of branch instructions. This one, conditional branch instructions. Depending on condition, you have to check condition to make a branch decision. Right? Taken branch, not taken branch. You have to check condition. So, and the second is unconditional branch instruction, jump instruction, right? Jump and link. So that is a format you are using, right? Conditional branch is using B type encoding, and unconditional branch is using J type encoding, right? And if you look at the encoding, the immediate, so immediate is a little bit, nasty, right? Because because of some, philosophy of RISC-V architect. Okay, RISC-V architect decided to use that encoding. So anyway, that is a little bit, nasty. Immediate 12, 11 is here, and 10 to 5, and 4 to 1. So in hardware, you have to rearrange. Once you have a machine code, you have machine code inside the CPU. Take out is 4 field, and rearrange, right? Rearrange means what? You just connect, right? Very simple, right? You have machine code. So bit 0 to bit 31. And then 7, OP code. Okay. Then immediate what? IMM 12. And then 10 to 5. So in the middle. So, and 11, right? Here you have 11, immediate 11. So what you have to do is, just connect, right? Okay, this one and this one like this. Rearrange. 10 is here. Using this wire, right? This 전선, really fine 전선, wire in Korean, right? 전선. You just rearrange, right? To make it nice and neat, right? Sequential. 12, 11, 10, and so on, right? So in hardware, you have to take out these 4, then these 4 immediate, and rearrange, right? Rearrange to make it, sequential. First, let's talk about BEQ instruction. So for BEQ, you have to do 2 things. BEQ. Example, for branch 2 this label, if condition, only if the condition is met. Okay, branch to here, otherwise you fall through. Taken branch, not taken branch. So to execute the branch instruction, you have to do two things. First one, branch destination computation. In hardware, you have to compute branch destination. What is destination? Program counter, location, right? Location, let's say location is 1. Location 1 plus sign extended immediate. So offset, right? How far you have to branch, offset. That is specified in immediate, right? So that is the first thing, branch destination computation. The first thing, right? Second, branch resolution. Taken branch or not taken branch? Taken, not taken. So you have to make this decision by comparing these two registers. These two are equal, taken. Not equal, not taken, right? So compare these two. So how do you compare? Probably comparison, right? Probably first thing you have to do is subtraction, right? You have to ask ALU to do subtraction. If the result is 0, ALU will do subtraction. If the result is 0, then that is taken. Equal, then taken, right? So program counter will be updated. Program counter will be updated with destination if the branch is taken. Two different things, right? So keep that in mind. Okay. So here, okay, branch destination, location, right? Location of branch, then sign extended, immediate. Okay. Remember this equation, 0, right? So that is specifying what? 12 to 1, not 11 to 0. Remember, 12 to 1, 12 bit, but 12 to 1. Okay. So you have to append, you have to add 0 here. Okay. First, let's design hardware for branch instruction. And the branch instruction is potentially updating program counter with the new destination. Okay. Taken, then update program counter with this destination. Otherwise what? PC will be what? PC will be PC plus 4. Branch is not taken, then as a user, right? Program counter will be updated to next location. So that means what? That means two candidate conflict, right? Another conflict. We have first candidate as usual PC plus 4 and second candidate are competing for program counter register, right? Two candidate. That is why I cut the line. So original instruction patch logic. Okay. So original path is that is connected to here. So PC plus 4 is updated to program counter register. And I cut the line because there are two candidates. Okay, two candidates. So conflict means you have to add multiplex. Okay. So here, how do you compute branch destination based on that equation, right? Location of program counter and sign extended. So we can use this logic, sign extension logic. Okay. And one special thing about branch is you have to add this 0. How do you add 0? Simple, right? This one, 12 to 1. You are supplying this immediate 12 to 1 to sign extension. and that will give you 32 bit, right? So 32 bit, right? 32 bit. You are just replicating, right? That guy. Take a look at immediate 12 MSB, then replicate 20 times, right? 20 times. So give you 32 bit immediate. Then what is this component? This component, 1 bit shift left for that purpose, for this purpose. 1 bit shift left, right? To fill LSB, least significant bit with 0. Okay, 1 bit left to shift. Okay, and then 1 bit shift left is super simple operation, right? Just 1 bit shift, right? Okay, then what do you have to do? That is sign extended immediate output, sign extended immediate. Then you have to add program counter. And PC is coming from here, right? PC, program counter. So you need adder, then program counter is connected here. Okay, then sign extend immediate. So adder output is destination location. Okay, so now we have to connect destination location and PC plus 4 to that guy conflict. So that means we need multiplexer. Connect like this. Okay, if you interpret this connection, PC plus 4, that connection. Okay, and then branch destination. Two guys are competing for this, one input, PC register input. Then adding multiplexer means what? You need control signal, right? Like this. PC source. Which is PC source? PC plus 4 or destination? Who do you think is generating that guy? PC source. Control unit? Not really, right? Control unit can provide that information? Not really, right? Because you have to do what? You have to compare, right? The decision should be made based on that comparison, right? These two are equal, then branch, right? Then these two are equal, then you select. Equal, then select adder output to PC. If these two are not equal, then PC plus 4 should be selected. So control unit cannot give you that information, right? So control unit can give you only that information. Can give you this information. Okay, instruction is BEQ instruction. Instruction is BEQ. Okay, then ALU should provide some information, right? ALU will do subtraction operation, right? Subtraction, right? These two. X3 supplied, okay, X4 is applied to. Then ALU should do subtraction operation if the result is 0. Get this output. If both, get this, if AND gate, if both inputs are 1. Okay, AND gate, right? AND gate. Both are 1, then output is 1. Both is what? Okay, it is branch instruction, BEQ instruction. And second input, okay, output is 0. So these two are equal. Then okay, so that will be 1. 1 means okay, you have to select a branch destination. Okay, any questions so far? Okay, last thing, unconditional branch instruction. Let me go back. to the slide to see the encoding. Look at this JAL instruction. Jump and link. It is unconditional branch instruction, right? Unconditional. And it is using J-type encoding. And then, it is very simple encoding, right? You have OP code and destination register and immediate. Okay. So if you remember the function of jump and link, right? X1, then jump and link foo, some function, right? This label. Okay. So you are jumping to this function subroutine. Okay, jumping, okay, jump to foo subroutine, then execute it, and you're supposed to come back, right? Jump and link. So that means the return location supposed to be saved in X1. X1 is a return of the RA register. RA. So think about this function. What do you have to do? What the CPU should do to execute that jump and link? First, destination location, right? Destination, PC plus same sign extended immediate. Okay, and then second thing is what? Return location, right? Let's say this one is 1000. Next location 1004. Right, next location this one. Okay? And X1, okay, should be updated with this 1004. 1004 is what? PC plus 4. Let's say PC plus 4. Okay, next location. Two operations should be done in hardware. Branch destination, right? Branch destination and return location, return location right? So that means what? So that means destination that is destination that goes to program counter, right? Then the schematic diagram should be looking like this. We have PC register, program counter register, right? Clock D and Q. Okay, PC. This is a PC program counter. Okay, and there are 3 candidates competing for this input. So far, we have PC plus 4. Okay, PC plus 4 want to go to here, and then branch destination like BEQ, right? We talk about BEQ. Also want to go to that there, and then jump destination. Also want to go to here. The 3 candidates competing for the same input. That means we need one more multiplexer. Right? One multiplexer is not enough, right? So let's go to next one, JAL. So here I cut this line again. Because we need one more multiplexer. 3 guys are competing, right? Competing for this one. So first jump destination computation. So we are using 20-bit immediate, not 12-bit. So we need probably one more sign extension logic, sign extension hardware, which is taking 20-bit input and generate 32-bit output. And then we need 1-bit shift left logic, right? For this purpose, right? 1-bit shift left 0. And then output should be added to program counter. Right? This one, if you follow this line, PC, okay, plus sign extended immediate. That is jump destination. This adder output, jump destination. So that guy somehow should be connected to this program counter register. So we need this multiplexer. See here, 2-to-1 multiplexer, right? and one more multiplexer. To refresh your memory, this one is PC plus 4. PC plus 4. And second, a branch destination. Okay. This adder is generating branch destination. And that guy, jump destination. Okay. Adding multiplexer means you need control signal like jump. Who do you think is generating that control signal? So in case of JAL, right? No condition check, right? No condition check. So control unit can provide this control signal, right? Like this, jump, by looking at OP code. Okay, then that is not it, right? That is not it. Okay, we have done the first thing. We have done first one, right? How about second one? PC plus 4 should be updated to register file. That is register file RF, right? So we have, register file conflict, right? Register file. Okay, here, if you look at carefully this multiplexer, we have one more input here, not two. One is ALU output, one is data from memory, and PC plus 4. This one, PC plus 4. So it should be, 4-to-1 multiplexer, not 3-to-1. There is no 3-to-1. There should be 4-to-1 multiplexer. So 0, 1, 2, 3. 0, 1, 2. So we are not using this, the last input. So this one, ALU, coming from ALU, this one is from memory, and this one is PC plus 4. That goes to register file, like this. All right. Okay, then adding multiplexer means, again, your control signal, right? Control signal you have to provide. All right, that is for today. As promised, we finished up CPU design. Any question? Role of multiplexer for arithmetic R-type. Why do we have to use multiplexer? While you can a bit more. Why do we have to use box while from? Samuel, hard to understand the question. So a question is about that multiplexer, right? This one. So to make it simple, let's go to here. Okay, this one is simple, right? This multiplexer, right? That is your question. If you have a conflict, then there should be some hardware component, right? You cannot connect ALU output without, think about that, without multiplexer. How would you connect ALU output to this input? Register file data, okay? And this connection, data output to here. Okay. So that is not possible to connect, right? Two different candidate, right? So we have register file, data input. You are writing something, right? And we have ALU, connect like this, okay? And memory, right? Data from memory. You cannot just connect like this. It is, you cannot connect like this, right? It is a wire, right? Johnson, right? Johnson. If you connect, think about that. It is just, for simplicity, let's say it is just one bit line, one bit, right? Then assume that ALU is driving this line to 0 volt, in other words. And memory is providing 1, okay, 1. Okay, 1 means what? 1 means, in digital 1 means, something like 1.5 volt. And 0 volt and 1.5 volt connected together. Then what is that? 0 volt, 1 volt connected together. There is a fire, right? Smoke, right? You cannot connect like that, right? So you have to have some, component like multiplexer. Okay, then connect like this, 0 and 1. Okay, so sometimes you want to connect that guy to here. Sometimes you want to connect this guy to register file, depending on control signal, 2-to-1 multiplexer. So think about your battery. You have a battery. What if you connect battery, right? 1.5 AAA battery. What if you connect directly to here 0 volt, 1.5 volt? What if you directly connect? Fire, right? Explode, right? Okay, thanks. Any other questions? Okay, I guess that's it for today then. See you. I'll see you on Monday. Okay, bye. Thanks.